Hi class, this is Professor Smith. I'm going to be doing a movie on using the rational zeros theorem to find all zeros of a polynomial irrational zeros. In this example, we have a function where we're asked to find at least one rational zero and use this fact to find all the zeros for the function f of x equal to 5x to the fourth minus 43x squared plus 43x cubed plus 51x squared plus 37x minus 14. If there's more than one zero, separate them with commas, and we're to write exact values, not decimal expansion. In order to use the rational zeros theorem, we have to determine P and Q. P is the constant term, which is negative 14, and Q is the leading coefficient. Since 5x to the fourth is the largest degree term in our polynomial, then 5 is going to be the leading coefficient. The rational roots theorem says take a look at all the factors of 14 over 5 and look at every possible combination. I will also go back and talk about using the opposites, but I'm just going to look at 14 and 5. So 14 has factors 1 and 14 and 2 and 7, and 5 has factors of 1 and 5. So we're going to look at all possible combinations. So we're going to take 1 over 1 and then 1 over 5. Then we're going to take 2 over 1 and 2 over 5. Similarly, 7 over 1 and 7 over 5. And then 14 over 1 and 14 over 5. So let's write out all those possible combinations. And remembering, we're also going to take the opposite of those numbers. So we have 1 over 1, which is 1, and 1 over 5, looking at the red marks. Then we have 2 over 1, which is 2, and then 2 over 5. 7 over 1, which is 7, and then 7 over 5. 14 over 1, which is 14, and then 14 over 5. And then, of course, all the opposites of those values are possible values for our rational zero. So, all right, plus or minus, meaning that plus or minus would be for each one of those values. So let's start off with 1 and use synthetic division to see if we have a remainder of 0. We're going to take the coefficients of our polynomial. Since it's in descending powers with no missing terms, we'll just take 5 from the x to the fourth term, negative 43 from the x cubed term, 51 from the x squared term, 37 from x, and then minus 14 is the constant. We bring down the 5. 1 times 5 is 5. When we add, we get negative 38. 1 times negative 38 is negative 38. When we add, we borrow from the 5 to get a 4, and 11 minus 8 is 3. 4 minus 3 is 13. 1 times 13, and we can see this isn't going to work. It's going to get too big. So it's going to be 49, and I need a 14 here in order to have a remainder of 0. So, bummer. We're sad. So x equal to 1 is not going to win. All right, so let's try negative 1, but I have a feeling we're going to get pretty much close to the same expression. Let's see. So again, we bring down that 5. Let me add another page so that I can capture this better. Excuse me, 5137. So let's try 1/5. Nor was 1/5, so let's try 2. No, we didn't try 7. So now we're going to do negative 1. And we have 5, negative 43, 37, and negative 14. Again, we'll bring down the 5. We get negative 5. This is worse. It gets a negative 48. So it's even larger. So that won't work. Multiplying by by 1/5 is equivalent to dividing by 5. So 5 divided by 5 is 1. When I add, I get negative 42. Negative 42 fifths. And then I need to multiply this term by 5 over 5. So I get 255 fifths. Ooh, minus 42 fifths. Now that is going to be 213 fifths. Oh my goodness, when I divide by 5 again, I'm going to get 213 over 25. So that becomes a hot mess real quick and is not going to be 14. And I believe negative 1/5 is going to yield similar results. So instead of having negative 43 and positive 1, it'll be a negative 1. So it's negative 44. And then you're going to get 44 fifths. And then when you get a common denominator of 255 fifths, now when you add them, that's even worse. So negative 1/5 is not a go. And let's go to another page to do the 2. All right. We didn't. Let's try. So we had 5, negative 43, 51, 37, negative 14. So we bring down the 5. 2 times 5 is 10. When we add, we get negative 33. 2 times negative 33 is negative 66. Then we're going to subtract 66 minus 51, and 15. 2 times 15, negative 15, because negative 66 is larger in absolute value. So then the sign will be negative. So 2 times negative 15 is negative 30. Ooh, hot dog! We get the desired 14, so we get a remainder of 0. So x equal to 2 is a rational 0. And therefore we have the quotient answer. Since the original polynomial was x to the 4th is the highest degree, then the quotient is going to be 1 degree less. So we have 5x cubed minus 33x squared minus 15x plus 7 is our resulting quotient. We want to find those zeros, so we're going to set it equal to 0 and solve for x. Since it's 4 terms, we could try pairwise factoring, and I notice, 5 and negative 15 have something in common, but 33 and 7 not so much. So then what we have to do is do the synthetic division again to find the roots of this new resulting polynomial. So in our particular case, p is 7 and q is 5. So the factors of 7 are 1 and 7, and 5 are 1 and 5. So all possible answers, just looking at the positives, but remember we'll check both the positive and negative. So we'll have 1 over 1 and 1 over 5. And 1 over 1 is just 1, but we already tried that. It didn't work in the original, so it surely won't work here. And we also tried 1/5. So both of those are a no-go. And then if we do the 7 over 1, but we tried 7 did we try 7? 7. All right, so 7 over 1 and then 7/5. So let's try 7. So we have 5, negative 43, 51, 37, and negative 14. We bring down the 5. 5 times 7 is 35. Negative 43 and negative 43 and 35 is negative 8. 7 times 8 is negative 56. Hey, we might be in something here. Here we get 50, so this is going to give us a negative 5. Yes, 7 times negative 5 is negative 35. And 37, and it gives us a 2. 7 times 2 is 14. So it does work. Hot diggity dog. So then we know that our resulting quotient will have degree 2. So it'll be 5x squared minus 8x. Oh, you know what? I wrote down the wrong thing. I didn't write down the original. is 5 negative 33. Let me erase that. I'm thinking something is terribly wrong. I went to the original, and we're on a new polynomial. We're on this one here, 5x cubed. So those are the coefficients I need to put in. So 5, negative 33, negative 15, and 7. All right, now we'll bring down the 5. 7 times 5 is 35. When we add, we get 2. 7 times 2 is 14. When we add, we get negative 1. And 7 times negative 1. Oh, that makes sense. If 7 went into the original, it surely will go into the quotient. So 7 would work. It's just that when I tried to write the descending powers, it didn't work. Yeah, I had too many terms. So here I have x cubed. So this one's going to march down one exponent. So this will be 5x squared plus 2x minus 1. And when I used the other polynomial, I had too many terms for a second degree quadratic. And now when we set this one equal to 0, we can try factoring it. However, if we use the AC method, multiplying a, which is 5, times c, which is negative 1, I'll get negative 5. And I ask myself, are there factors of negative 5 that add up to 2? And the only factors of negative 5 are 5 and 1, changing the sign, one of them being negative. So you can either have negative 5 and positive 1, or you can have positive 5 and negative 1. Neither of those are going to give you a 2. And so that's why this section is called irrational zeros. Once we get to that quadratic, it's not going to factor, so we have to solve it another way. So let's add another table to solve that quadratic. So we have 5x squared plus 2x minus 1 equal to 0. And so we could complete the square, or we could use the quadratic formula. So the quadratic formula says we've got to first determine a, b, or c. A is the coefficient of the leading term, or the second degree term for our quadratic, so it would be 5. B is the coefficient of our linear term, which would be x, so the coefficient of that is 2. And then our constant is negative 1. The formula says that x is going to equal the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So you get the opposite of 2 plus or minus the square root of 2 squared minus 4 times 5 times negative 1 all over 2 times 1. Be sure when you're using the quadratic formula that you extend that division bar over both the terms, the negative 2 and the discriminant, or the square root of the discriminant, that square root part. All right, so now we're going to simplify. So we have negative 2 plus or minus the square root of 4 minus, now I have a negative 4 times a negative 5 all over 2, which is equal to negative 2 plus or minus the square root of 4. Negative 4 times negative 5 is a positive 20, so that's 4 plus 20 over 2. So that gives us negative 2 plus or minus the square root of 24 all over 2. It turns out square root of 24 has a perfect square trapped inside. 24 can be written as 4 times 6. And so since 4 is a perfect square, I'm going to rewrite it first. So let's do that on our next page. So I have negative 2 plus or minus the square root of 24 all over 2. And I'm going to rewrite that 24 as plus or minus the square root of 4 times 6 all over 2. There's a rule that says if you have the square root of a product just means two things multiplied together, you can take the square root of each piece and multiply them. So minus 2 plus or minus the square root of 4 times the square root of 6 all over 2. So the square root of a product is equal to the product of the square roots, provided both the 4 and the 6 are positive. Actually, it does work for complex numbers, but for now, we just want to use it for not necessarily. So just whenever they're positive, that rule applies. The square root of 4 can be simplified. It's equal to 2 because when you take 2 and square it, you get the 4. So the square root of 4, which is the positive square root, is going to give us 2. So this is simplified as negative 2 plus or minus 2 root 6 over 2. And you say, well, why couldn't you just leave it as root 24? I'd have been happy with that. Well, it turns out when we simplify it, we can see now that the 2 that's in the denominator will divide into the negative 2 that's in the numerator, as well as the 2 root 6. So you can think of writing it as negative 2 over 2 plus or minus 2 root 6 over 2. Negative 2 over 2 is negative 1 plus or minus root 6. Another way to think of it is you could factor out a 2. So if you factor out a 2 in the numerator, you get a negative 1 because 2 times negative 1 will give us the negative 2 here. And then plus root 6. And 2 times root 6 will give us the 2 root 6 here. All over 2. And again, that's plus or minus. Now I can cancel the 2's because I have a product. So I'm going to cancel the 2's, and I have negative 1 plus root 6. So either way, you can divide each term by 2, or you can factor and cancel. So plus or minus, pardon me. So our two answers are x equal to negative 1 plus or minus root 6, which Alex will take the answer written that way. It has a plus or minus symbol. We also had a x equal to 2 and x equal to 7. So we see here that we have 4 real roots of this polynomial. So I hope this video on finding the zeros of a polynomial, irrational zeros, was helpful for you.